1 second. So, ठीक है, we were stuck at this question. ठीक है, इसके बाद my internet went off. Starting with this question, it's the same paper. इसमें the first thing is, what's the role of this thing, this thiosulfate thing? So I'll just give you a brief a background on. So let me add people. So I'm just going to give you a brief background on solubility. K. What is this square thing? It does appear sometimes in AS, but it's mostly in A2. This thing with square brackets, that's known as a complex ion. Just a very brief overview of what this is. Complex ions are ions that are formed when something resolves. I mean, for example, if you have NaCl, and remember, it's just going to be a simplistic overview of this thing, not a detailed overview. You don't need to know any details about this. So when NaCl dissolves, it turns into Na+1 aqueous and Cl-1 aqueous. Now, the only thing is that Na+1, when you see Na+1 aqueous, Na+1 is not just floating around in water alone. What it's actually doing is that it's attracting water molecules from all sides. So for example, if these are your X, Y, and Z axis, so this sodium ion, if it's in water, it will be attracting, because water molecules are polar. So it will not only be just attracting water molecules, the negative oxygen, but a dative bond would form. The water molecule would be very strongly bonded to the sodium ion. Not very strongly, but the lone pairs of the water would be attracted to the sodium ion. And this would happen from all sides. You'll have water molecules and they will be attracted to sodium ions. So that results in the formation of a complex ion. For example, if I look at copper sulfate, for example, if it's dissolved in water, so 1 second, let me just Google this. I'll get an image of a. So for example, this one. Okay, this one. So this kind of is a better view. So when copper ions are dissolved in water, and whenever you say copper ions aqueous, you're actually referring to this ion. Copper ions attract the lone pairs of water molecules from all sides, and they end up forming a complex ion. Complex ions are referred to as, they put in these square brackets. So for example, the way you're going to write this is going to be copper with 6 water molecules, and you'll put a square bracket around it. That would indicate the net charge on the ion, which is going to be +2. So the square bracket thing is complex. It's a complex ion that is formed, and this has always happened. So whenever you think of copper 2+ aqueous in solution, or Na+1 aqueous, or NaC, or any ion that's aqueous, it's actually attracted to those to the solvent. So the water molecules are kind of acting as something that helps in dissolving the copper ions, because if there was no water molecule, then copper ions would obviously not dissolve. So if we come back to this question, and let me clear this. You just need to know a very brief general overview of this. No detailed questions, it's in A2. So if we go back to the question, you can see over here, what he's saying is that there's a complex ion that's getting formed. So the silver ions are getting, he's saying the unreacted silver bromide is removed by reaction with sodium thiosulfate. So the whole role of sodium thiosulfate, or these S2O3- 1 ions, these one over here, was to make the silver ion soluble. they help in dissolving the silver ions. So that's the role that they are playing. So just a brief general idea of what a complex ion is. Whenever you see one, that means the silver ions are actually dissolving with the solvent, and these are helping it dissolve it in solution. Is this point clear?
Yes.
Okay. But just a general idea, okay? Nothing more detailed. Whenever you see a complex ion, that just shows it's dissolving. Now this one, starting with organic questions now, people who make statin drugs to control their blood cholesterol may also take this thing. The diagram shows a simplified structure of one of this coenzyme. Which row describes this structure correctly? The coenzyme is an aldehyde or a ketone. So the double bond is right in the middle. I mean, it's got two ketone groups. So it's obviously a ketone. So it's either C or D. The other one is number of pi bonds in one molecule. Now, this square bracket shows that this thing is repeating n number of times. I mean, after this point, there's just it's just constantly repeating, and then you've got an H at the end. So it's got how many double bonds? It's got one over here, and it's being multiplied by n, so there would be n double bonds. Each double bond, remember, each double bond has one pi bond. So that means they're going to be n pi bonds over here. Then there's a pi bond here, a pi bond. Every double bond has one pi bond. So it's got 4 pi bonds over here. One over here, one over here, one over here, and one over here. Remember this, every single bond is just sigma. Every double bond is made up of 1 sigma plus 1 pi. And every triple bond is going to be made up of the first bond is always a sigma, and the rest of the 2 bonds are pi bonds. And I'm just going to quickly show you how N triple bond N is formed, just to give you an idea of this. Nitrogen has this electronic configuration. At the end, it's got 3 orbitals that need electrons, 2py and 2pz. So nitrogen's case, there's going to be one orbital, let's say on the x-axis. So there's one nitrogen atom and there's another nitrogen atom. They both need electrons, so they're going to end up overlapping above and in the middle. That's a sigma bond. So one of the nitrogen atom, its px orbital would bond with the other nitrogen atom px orbital. So let's say, so there's overlapping and the middle part gets filled up. The electrons get stuck in the middle. Then the 2py of one atom, so this is the y-axis, and the 2py of the other atom, they would start overlapping and they're going to form a pi bond. Their overlapping would be above and below. And then you've got a 2pz as well. So the 2pz would be on the z-axis. So that indicates that there's going to be overlapping that would be happening in the front and on the back side. So there's going to be overlapping that would happen in the front and the backside on the z-axis. So there would be 2 pi bonds formed. The first bond is always a sigma bond whenever you've got a triple bond, double bond, or a single bond. The next of the bonds are always pi bonds. So between 2 atoms, the first is always sigma. The rest, once the middle part is occupied with electrons, so the middle part already has electrons, then all the other bonding would happen above and below, or from the front or the back. Okay, is this clear?
Yes.
So इस case में there's going to be n plus 4. There would be n pi bonds over here, because n number of times it's getting repeated. Plus there are going to be 4 pi bonds over here. 1 pi bond in each double bond. Let's do question 21. Case, what is he saying? He's saying, I mean, this is kind of easy. What type of isomerism is this? Can anyone answer this?
Cis trans.
Okay, so this is obviously cis trans because this double bond can't form cis trans. The other one is forming cis trans. This one over here. The only thing is that the for cis trans to happen, both groups attached on this side must be different and on this side must be different as well. So over here, the H is pointing downwards, and over there the H is pointing upwards. So the direction of the H is switched. I mean, these two have different directions over here. So that is obviously geometric or cis trans. So then we can move to the next one. 1 second. The next one is about polymerization. He's saying, what is the identity of the monomer that produces this polymer? So all you have to do is you have to find the repeat unit, which is, I think, this one. That's the repeat unit. You redraw this, take it out, and put a double bond in the middle. The connections are gone. I mean, these bonds over here, they're gone. So the connecting links are gone. This is repeating over and over again. You put a double bond back over there. So we need to name this. It's a question more about naming. So can anyone tell me what the name is of this molecule? Like, what's the longest chain? How many carbon atoms?
3 carbon atoms. No, 4 actually, 4.
Okay, so let's take this one. This is 4 carbon atoms. So that is definitely bute. And where's the double bond? Second or third or first? What position?
Sir, 2 chloro and 3 methyl.
Okay. And bute what? Well, the एक ही option होगा, that's butene, right?
Yeah, butene.
Okay. I mean, the green part is butene, and then you've got 2 chloro and 3 methyl. Okay. Remember, chlorine is slightly more important compared to alkyl groups. Okay. Remember the precedence as well. If you have multiple functional groups, where's the organic nomenclature? Just a second. Okay, कौन से group को numbering करना है? Which group has to be given a better? Let's just open the Wikipedia page. So remember the precedence, okay? Where's the precedence? Just a second. Order of precedence. So remember, carboxylic acids are kind of the most important. Okay? Whenever you have a carboxylic acid, that is always given the smallest number. Usually it's 1. Then you've got these other things. You've got esters and amides, then nitriles, aldehydes, ketones. That's the order. And then you've got alcohols. And at the end, it's amines. Okay? So remember the order. Naming for nitriles is not that important. Remember carboxylic acid. If you've got multiple functional groups, carboxylic acid is supposed to be given the smallest number. Esters and amides, their naming is completely different. Then you've got aldehydes and ketones, alcohols, and amines. So if you have an aldehyde and a ketone and an alcohol, the smallest number must be given to the aldehyde. Because remember the precedence of these groups. So the next one is it's butene 1,4-diol is converted into 2 steps through an intermediate X into oxobutane dioic acid. What could be the reagent for step 1 and what is the intermediate X? So this molecule is getting converted into this molecule. Let me just draw the, I mean, it's got 4 carbon atoms. So that's 1, 2, 3, and 4, plus there's a double bond in the middle. And there are OH groups right at the end. So there's an OH here and there's an OH over here. And just forget there would be 2 hydrogens, 1 hydrogen, 1 hydrogen, 2 hydrogens. The final one is again 4 carbon atoms, except that it's got carboxylic acids at each end. And it's got a CO on the second carbon atom over here. So there's a CO group, which is C double bond O, and the rest is just CH2. And just you're turning this into this one. So there's obviously oxidation involved. Oxidation is involved because the OH over here turns into a carboxylic acid, which is this one. So that is happening, oxidation is happening in this step. So how do you turn, so the middle step, KMNO4 is involved over there. Now over here, so you don't need KMNO4 over here. The middle part needs to be turned into a ketone. There are two ways of doing that. There's actually a single way of doing that. You just need one ketone. You can either have, you just need one ketone. So what you can do is, you can add a water molecule. Alkenes don't have a lot of reactions. They just have addition reactions. So what you can do is you can add a water molecule, an OH and an H will get added. And this would be called hydration. So water would be added. And that's a secondary alcohol. If you look carefully, the carbon is bonded to two carbon chains. So that one is a secondary alcohol, and you can convert that secondary alcohol into a ketone. Remember secondary alcohols? The only oxidation they have is up till ketones. Primary alcohols can be converted to aldehydes, and which would further get oxidized to carboxylic acids. So all you need over here is steam. The condition for hydration of water is 60 atmospheres. 300 degrees centigrade is the temperature, and you need a acid catalyst. Usually it's phosphoric acid, but you can use any acid. Like in this case, he's using concentrated H2SO4. So those are the conditions for hydration. And this molecule would be formed, which is option C. ठीक है, ये भी clear है?
Yes, sir.
So then you have another one, which is hydrogen bromide can be added to T to give compound U. Compound U can be hydrolyzed to compound V. So this is happening. He's saying 4 students, W, X, Y, and Z made the following statements. So the first one is W, all the atoms in the molecule of compound T lie in the same plane. Well, they will not lie in the same plane. W to वैसी गलत है. Why? Because these two carbon atoms are the only ones that are going to be trigonal planar. Because whenever you have carbon making double bonds, the shape is fan shaped. I mean, it's literally going to look like this, the way it's drawn on paper. The rest of the molecules or the rest of the bonds are going to be these carbon atoms. They would be tetrahedral. Okay, all of them. They're going to be tetrahedral. What's a tetrahedral arrangement? Okay, they would not lie in the same plane. For example, over here, there's going to be, I mean, this is carbon. There would be an H. There would be one H that would be going into the page. There's going to be one H that would be coming out of the page. So it's going to be a tetrahedral arrangement. Whenever carbon is making single bonds, it's tetrahedral. So, sorry. So this one is definitely incorrect, that they'll all lie in the same plane. Okay, that's wrong. Next one, compound V contains only one chiral atom. So this one. For chirality, you need 4 different, you need a mirrored, carbon is going to have mirrored versions, and optical isomers known as enantiomers, and that could only happen if carbon is bonded to 4 different groups. It needs, there should be no symmetry. All 4 groups must be different. Only then would the mirror image be a different non-superimposable mirrored version. So this one is chiral because it's got 4 different sides. One side is different, one side is different. This carbon chain is different, and this carbon chain is also different. This other one is also chiral because in the skeletal formula, they're not showing the H, but there is definitely an H atom attached. And again, all 4 sides are different for this as well. The top is CH3. This side is a carbon chain. This side is a carbon chain as well, which is different from the one on the left because you get different functional groups over here. So all 4 sides of this carbon atom are also different. So they're actually 2 chiral centers. So X is also wrong. Is this clear?
Yes, sir.
Yes, sir.
ठीक है, और ये वाले chiral नहीं होंगे because they would be bonded to 2H. So for chirality, you need all four sides to be different. So only two chirals. As the next one is step one is electrophilic addition reaction, which is true. Why is true? Okay, it is electrophilic. Okay, I think hydrogen bromide is being added to an alkene. So that is what happens. Okay, when you have a pi electron cloud over here, there's a very large electron density over here, and the electrons of the bond over here are going to get repelled. This would become negative, this would become positive, and the positive H will be attracted, will be an electrophile, and that would lead to electrophilic addition. Alkenes always have electrophilic addition reactions. Step two is nucleophilic substitution reactions, which is also true. That is an SN reaction, and to be very specific, that is a tertiary halogenoalkane. Okay, I'm just going to quickly revise what all of these were. Just 1 second. So I'm just going to go through, if I can. I said this one. Yes. So the thing was that when you have a halogenoalkane, it's always nucleophilic substitution. Like the carbon has a positive charge, it's already polar because it's attached to an electronegative halogen atom. So since it's polar, it's positive. I'll try to send them. I'm going to try and send them on WhatsApp. Let me just write it somewhere. I saw this one. We've got carbon, which is positive, and this is a primary halogenoalkane. For that, it's SN2 mechanism. The thing is that since it is positive, it has a positive charge. What happens is that the CN -1, it doesn't really happen exactly like this. Let me just remove one of the carbon chains 1 second. Let's get rid of this. So what happens is the nucleophile, it's either CN -1 or OH -1 or NH3. They get attracted to this carbon, which is positive because of the polarity in the bond. And the Cl gets repelled. It's going to take away the electrons. So the OH -1 is going to come in and the Cl is going to be pushed away. So for example, I'm over here, I can change this to OH -1. So a transition state is formed. The OH starts to bond with the carbon and the Cl starts to get repelled. Eventually the OH is going to join up. So that's the mechanism of the reaction. That's nucleophilic substitution, and it's called an SN2 mechanism. The thing with this is that the OH immediately bonds with this carbon atom because the carbon has a pretty strong positive charge. I mean, this carbon atom has a really strong positive charge. And the reason for that is that it's not bonded to large groups. I mean, on top, there's a hydrogen atom. Hydrogen doesn't really have a lot of electrons. Similarly, at the bottom, there's a hydrogen atom. Again, it doesn't really have a lot of electrons. So the carbon, positive charged carbon, is not really surrounded by large groups. So the OH -1 has a pretty strong attraction to this carbon. So it immediately comes in and knocks the Cl away. When you have a tertiary halogenoalkane, this time carbon is surrounded by carbon chains in a tertiary halogenoalkane. I mean, for example, you've got alkyl chains on all sides. So if you have alkyl chains on all sides, the positive charge on this carbon atom is not very large, because if there is a positive charge, there are lots of electrons around it. There are large groups around it. So the electrons are going to be attracted to the positive charge, and the positive charge would kind of in a way get neutralized. So the positive charge is not very strong. Now, in this case, the nucleophile is not going to be attracted initially to the carbon. The Cl would have to break away first, and then a carbocation would form, and then the Cn-1 would come in and bond with it. So it's a two-step process. Over there, the positive charge was very strong, so the nucleophile immediately got attracted. But over there, the positive charge is not very strong. But anyways, you've got SN1 and SN2 mechanisms for halogenoalkanes. So coming back to the question, since it is a halogenoalkane, this would be nucleophilic substitution, and this would be specifically, it would be SN1 mechanism. So which two students are correct? So it's probably going to be Y and Z. These two students are going to be the ones that are correct. Okay, is this clear?
Yes,
Yes.
sir.
अच्छा, फिर है कि you've got this one, question 25. You've got he's saying structural and stereo both. Okay, so he's looking for both. They should be considered. A compound J is reacted with KOH dissolved in ethanol. So 3 isomeric alkenes with molecular formula C4H8 are formed. What is J? Now, halogenoalkanes undergo another reaction, and that is, I'll open a spider chart for this so that you can kind of see. I'll send that spider chart as well. 1 second. Let's do this one. Make sure you have a chart like this with you at all times, so that you can know what would a halogenoalkane do when you react with KOH. So halogenoalkanes. I mean, is this AS? So this one. These are your halogenoalkanes. So you've got KCN and ethanol, so all sorts of stuff is happening. This specific reaction, a halogenoalkane turning it back into an alkene. If you use sodium hydroxide or KOH in ethanol, this is what would happen. An elimination reaction would happen. The halogenoalkane would turn back into an alkene. So I'm going to keep referring to this one. So the halogenoalkane would turn back into an alkene, and an alkene would be formed. So this is what's going to happen in this case as well. And the alkene is going to be formed in this way. You've got 2 carbon atoms. As you've got 2 carbon atoms. And let me just draw a better version of this, showing all the bonds. From one of the carbon atoms, a Br would be lost. From the neighboring carbon atom, an H would be lost, and they would end up forming a double bond over here. Similarly, the second one. That's for the first one. An alkene would be formed, which would be but-1-ene. The double bond would be at this point. What about the second one? Okay, you have 4 carbon atoms, and you've got a Br over here. Now, the neighboring carbon atoms are 2. The H could be lost from this point, or the H could be lost. I mean, the Br would be gone, but the neighboring carbon atom H would be lost. So the double bond might appear over here, or it might appear on this side. So you've got 2 options over here. It could either be but-1-ene, or the second option is that it could be but-2-ene. Okay, is this point clear that you've got two options for the double bond? Because the Br is in the middle. Is this clear?
Yes, sir.
Yes.
So now the third one, same thing. Third one is you'll only get there's only so the third one is the Br is over here. So the neighboring carbon atom is just 1. So the H would be lost, Br would be lost. So the double bond, there wouldn't be many positions, just 1. And for the fourth one, it's again just going to be one position. Like the H is here, the Br would be lost from one atom and the H would be lost from the neighboring one, and it would form a double bond. So in this case, it wouldn't really matter whether the double bond is here, here, or here. That would mean the same thing. So which one would form three versions? And he was very specific. You're supposed to look for stereoisomers as well. Now we're going to go with B, because B clearly forms two structural isomers. I mean, that's fairly obvious. It's forming two structural isomers. And if I add in the hydrogens, this would be CH2 and CH3. Achha, for this one, there would be no cis and trans. Why? Because the double bonded carbon atoms, they're bonded to the same groups on both sides. This one will have cis and trans because this one will have cis trans because the double bonded carbon atoms, the carbon is bonded to two different groups and this carbon is also bonded to two different groups. So this one will have two versions. The first one won't have cis trans, this will have two versions. So in total, you're going to have three different versions. The first one, this one will have just one version. So that's one. And this one will have two versions. It's either going to be a cis version and or a trans version. So in total, you're going to get three different alkenes. Ye clear?
Yes, sir.
Yes, sir.
So Aglawala Sanik, you just need to spot primary, secondary, and tertiary. So this is primary. Look for the alpha carbon, the one. Secondary is it's bonded to two carbon chains. Tertiary would be if it's bonded to three carbon chains. So that was easy. Now, the fragrance of compounds or perfumes are often dissolved in solvent Y, which has the molecular formula C7H12O4. It is made by reacting propane 1,2-diol with ethanoic acid in the presence of an acid catalyst. So this is fairly obvious. It's going to form an ester because this one is an alcohol and it's a diol. It's got two alcohol groups. So reacting it with ethanoic acid, what would happen? The H would be lost and the OH would be lost here. And a propanoic acid would also react from this side. So an ester is formed when OH is lost and H is lost. And they're going to end up forming a bond. I mean, this carbon atom over here would form a bond with the oxygen. This carbon atom over here would directly form a bond with the oxygen over there. The water molecules would be removed. So which one is the correct option? It's probably going to be this one, I think. CH3 C double bond O, CH3 C double bond O. The other side is CH3 C double bond O as well, followed by an O, followed by an O. Okay, so it's D. So remember how to make esters. Next one is again about esters. He's saying which mixture could be used to produce propyl methanoate. So for this, you need to know, first thing, you need to know the naming of esters. Esters have this functional group in the middle. Now, propyl is three carbon atoms. The wild side or alkyl side is the one that's connected to the single oxygen over here, single bonded oxygen. And the other side is methanoate. So there's already one carbon atom there. The rest are all hydrogens. So who's going to make this? Now we're going to break the ester. So if we break the ester in the middle, this side turns back into a carboxylic acid. It would be C double bond O and OH. While this side over here will turn into an alcohol back again. And this would be CH3, two hydrogens, and this would be two hydrogens as well. So the correct answer would be C. You need methanoic acid and you need propanol. Okay, is this clear?
Yes, sir.
Yes, sir.
As a play, you've got which statement about polychloroethene is correct? The polymer can be cracked. First thing, chloroethene. Ethene is 2 carbon atoms. I mean, this is PVC. It's chloroethene is this thing. When it forms a polymer, the double bond would break and linkages would form. And there's not going to be any double bond in the middle. So the polymer can be cracked to produce chlorinated alkenes, which is true. Like if you do the reverse and you crack the polymer, you're going to get alkenes, which would be like this. So the polymer can be cracked to, so I think that's true. It definitely doesn't have harmless combustion products, like carbon monoxide could be produced, HCl could be produced. The polymer is not readily biodegradable. Remember, addition polymers, most of them are not. Okay, whenever you have an addition polymer, they don't biodegrade. So they don't biodegrade, and the reason is that the carbon chain is very stable. The carbon is nonpolar. When something is nonpolar, it doesn't really attract anything else. So in an addition polymer, most of the carbons are just lined up in a straight line. And those carbon atoms, it's very hard to actually break them because nothing usually reacts. They're very unreactive. And the repeat unit of the polymer has an MR of 97. I don't think that's 97. This is a lot less than 97. The repeat unit, it's got 2 carbons, that's 24, 35, and 3. So I don't think that's 97. So the first one kind of looks to be correct. Acha, phir kaun sa hai? Again, that's the third question about esters. So he's saying increasing number of carbon atoms. Remember, esters have names where you just number the carbon atoms on both sides. So one side is eth, the other side is meth. So that's 2 plus 1. This would be 1 plus 3. This would be 5 plus 5. And this would be 5 plus 4. So I mean, it has to be increasing number of carbon atoms. Over here, the numbers have decreased. So what about B? It's 2 plus 1, 1 plus 3, so that's increasing, 3 plus 4, and 5 plus 5. So it's going to be, B is correct. It is increasing. It's 3, then 4, 7, and 10. Okay, is this also clear?
Yes.
Yes, sir.
Which molecules have an overall dipole moment? So first thing, it has to be an electronegativity difference. You do have oxygen is very electronegative, so that's partial negative. This is partial positive. Sometimes you get questions about this, that even though this bond is really strong, but carbon monoxide is very unstable because it's polar and it attracts other molecules very, very strongly. Nitrogen also has a triple bond, but that's very inert. The reason it's non-polar. So remember, carbon monoxide has very high polarity, which is why it's very unstable. It reacts with it gets attracted to many things. As a phosphine is going to be polar because of its shape. Because group 5 will have lone pairs sitting on top. So the overall dipole would be that phosphine would be pulling electrons upwards. The top of the molecule would have a slight negative charge. The bottom of the molecule would have a slight positive charge. Carbon dioxide is the one that's non-polar because even though there's a difference in electronegativity, but because of its shape, the dipoles are going to get cancelled out. So overall, it's not going to have any dipole whatsoever. Ye be clear?
Yes, sir.
Yes.
So this one is easy. It's Hess law. So he's saying Hess law is if you want to go from T to S, the enthalpy change would be the same no matter what path is followed. You take this path or you take this path, the enthalpy change would be the same. So the enthalpy change for the transformation U to R is 42. So we have to go from U to R. So I'm going to take this route. So it's going to be minus 92 because I'm going in the opposite direction of the arrow. And it's going to be plus 134. So that would give me plus 42. So that is correct. Then T to S is endothermic. So you're going from T to S. I'm going to take this route. So it's going to be minus 75 and minus 92. Again, because I'm going in the opposite direction to the arrow, I'm going to change the sign. So instead of plus 92, it is now minus 92. So both values are negative, so that's going to be exothermic. If the second is wrong, the third would also be wrong. And we can calculate that. You're saying R to T. So R to T is, so for R to T, you would have to go all the way in this direction. That is R to T. So it's minus 134 plus 92. And the last one is plus 75. So I think it's going to be plus 33, not minus 33. TK, is this clear as well?
Yes.
So this 133. You've got a reversible reaction. First statement, an increase in concentration of a reactant always increases the concentration of a product. Is that true? If I increase the concentration, where would the equilibrium shift?
To the right side.
Okay, so it's going to shift to the right. So what would happen to the products? They would increase. And that would always happen. Okay, so that is correct. An increase in temperature always increases the rate at which the equilibrium is established. And so now remember, as soon as he mentions rate, remember, be very careful because people confuse rate with equilibrium. As soon as he mentions rate, then the question is no longer about equilibrium. It's not about the reaction moving forward or backward. It's just a rate question. Even though he's using the word equilibrium, but if he's talking about the rate of the equilibrium, then it's basically rate. So it should have nothing to do with the reaction moving forward or backward. So what happens if you increase temperature? Does the rate increase? And
yes, sir.
So it's obviously. And the rate would increase of both forward and backward, no matter what the reaction is. Pick any reaction in the world. If you increase the rate, if you increase the temperature, the rate would increase both forward and backward. Remember, एक चीज का ख्याल रखना है कि when you talk about equilibrium talks about forward and backward in relative sense. I mean, when it says that the forward is favored, that doesn't mean that the backward is slowing down. It just means that the forward reaction is faster comparatively compared to the backward one. Maybe they're both slowing down. Maybe they're both speeding up. So a comment on equilibrium or the position of the equilibrium is not a comment on the rate of the reaction. It's just a comment on which out of the two, which of the reactions is faster. So whenever you change any conditions, and when you use the words like equilibrium position shifts to the left, or the backward reaction is speeding up, or the backward reaction is favored, that doesn't really mean that the backward is speeding up. It just means that the backward is speeding up compared to the forward one. So maybe they're both slowing down, maybe they're both speeding up. That is determined by the rate of reaction, whatever you've studied in rate of reaction. So the second statement is correct. An increase in temperature always increases the concentration of the product at equilibrium. So when I increase temperature, so for example, let's have, which reaction would be favored?
Both.
Which, remember, he's saying, I'm talking about the equilibrium position now. Both would be favored. I mean, when you increase temperature, both reactions would speed up. But I'm talking about equilibrium. Which one would speed up more when you increase temperature?
Forward.
And what was the rule for equilibrium? When you increase temperature, which reaction is favored? It's the endothermic reaction. Okay. The one that's endothermic, the one that needs energy, that would speed up more. Is this clear?
Yes, sir. But here it's not specified which is endothermic and which is exothermic.
So exactly. So how would you know, okay, it's going to be the products? So that, because he was using the word always. So maybe products might be favored, but not always, TK, because it has to be the endothermic reaction. We don't know which one is the endothermic in this case. So that part is wrong. Okay. So I'm just going to restate this. Be very careful whether he's talking about equilibrium or whether he's talking about the rate of reaction. Okay. So when he's talking about equilibrium, you decrease temperature, which reaction is favored? Exothermic is favored. Or फिर ना आप ऊपर जाके what you do is you just find out which one is the exothermic or which one is the endothermic. But the comment on equilibrium is just simply a comment on which reaction is faster compared to the other one. It's not a comment on the actual speed of the reaction. It just means that one of the reaction is relatively faster compared to the other one. The same question is about rate, then if you increase temperature, both reactions would speed up, but one of them would be relatively faster. That's what equilibrium would decide. If you increase temperature, both reactions would speed up. The speed would be higher. But whenever you increase temperature, the endothermic reaction would be favored. So the one that is endothermic, that would be slightly faster compared to the other one. So next one is a chemist puts a sample of dilute. Is this clear? Yes.
I just wanted to ask about the second point here. It is saying that like the rate at which equilibrium is established. So like, doesn't it mean that the time taken for equilibrium to establish? So that would. Yeah.
That depends on rate, right?
Yeah. So you were saying the same thing basically, that it will take less time when temperatures increase. Yeah. Okay.
So next one, 34. Chemist puts a sample of dilute hydrochloric acid into beaker 1. She adds a sample of zinc and measures the rate of the reaction. So it's zinc with hydrochloric acid. So that would produce zinc chloride plus H2. She then puts a different sample of dilute hydrochloric acid into beaker 2. So the only variable I think in this case is HCl. She's using a different sample. So two samples, two separate experiments, beaker 1, beaker 2. And she adds a different sample of zinc as well and measures the rate of production of hydrogen gas. So I think she's using a different sample of zinc as well. So the rate of the reaction in beaker 2 is greater than the rate of reaction in beaker 1. Which factors could help explain this observation? So the reaction in beaker 1 has a higher activation energy than the reaction in beaker 2. Is that true? Like, it's the same reaction, right?
Yes.
So obviously, why would the activation energy be different? The activation energy would be the same. The activation energy changes with one thing only. And what is that one thing?
The catalyst.
So that is the only thing. It's increasing temperature. Doing anything else will not affect the activation energy as long as it's the same reaction, which in this case, it is the same reaction. So if one is wrong, 2, 3 are automatically correct. Zinc in beaker 1 is in larger pieces. So that's why the reaction is slow. That's obviously slow. Powdered, if it were in smaller pieces or powdered, the reaction would have been faster. The acid in beaker 1 has a lower concentration. Again, that's the reason why it's slow. So that also makes sense. So 2 and 3 are correct. So then you've got in some rice growing parts of the world, farmers use a combination of paddy fields and fish. Rice paddy fields are flooded for much of the growing cycle, and water running off the fields flow through the pens where fish are raised. Nitrogen-based fertilizers are generally very soluble in water, which problems could result from farmers applying excess nitrogen-based fertilizers to their paddy fields. Remember, it's eutrophication. What would happen to the water, to the fish water, it's going to be eutrophied because there would be too much algae growth. So decrease fish production in the fish bin. So there's going to be algae growth, and sunlight will not be able to enter, and bacteria would grow on the dead algae and the dead plants. There's going to be decreased levels of oxygen as well. I think all three are correct. Clear? It's O levels eutrophication.
Yes, sir.
So now 36 is a sample containing 0.4 moles of calcium nitrate was decomposed in a roaring Bunsen flame until there was no, so it's getting decomposed. And calcium nitrate, when it gets decomposed, it produces 2NO2.5 O2. So the question is, what are the products of the reaction? He's given us the moles as well. So it's 0.4 moles. So calcium oxide would be 0.4 moles as well. NO2 would be 0.8 moles. And this one over here would be 0.2 moles. So what are the products of this reaction? So the first one is correct. The second one is wrong. And the third one is also wrong. So all you needed to know about this was, if you knew the equation, you would have been able to do this. Now 37, which reagents when used in excess can be used to make sodium lactate? This one from this thing. So you're trying to convert this to this. So this compound has two things. It's got an alcohol and it's got a carboxylic acid. So it's got both functional groups. Which one would Na react with? OH or carboxylic acid?
Both.
Okay, remember, Na alcohols are extremely terrible acids. I mean, they don't like to ionize, but they do ionize very, very weakly. You can't even classify them as acids, but they tend to react very slowly with Na. And the H at the end, carboxylic acids are obviously acids. So they're going to react as well. So which is why that's not possible. We don't want the OH to react. Okay, so you can't use Na. The rest is fine. Alcohols don't have any further acid reactions because they don't like to ionize that much. So you've got carbonates and hydroxides. They would react with the carboxylic acid because carboxylic acids are complete acids. They have all typical acid reactions. So the carboxylic acid are your typical acids. So 2, 3 are correct. It's going to be, yes.
I do understand about the sodium one. The
sodium.
one.
So alcohols are, I mean, they like to ionize very, very weak. I mean, what reactions have you studied about alcohols? You've studied about mainly about oxidation of alcohols, TK. That primary alcohols, secondary and tertiary alcohols. You didn't do any mechanisms with alcohols, TK. There was mostly oxidation and their formation, TK, like hydration of alkenes or dehydration of alcohols to turn back into alkenes. But mainly it was just oxidation of alcohols that you studied. But there was one other thing that you studied in alcohols, and that was that alcohols tend to ionize. The OH at the end releases an H+1 ion, but it's a very weak ionization. It's even less than water. So their acidity or their ability to produce H+1 ions is really bad. So normally acids react with metals. I mean, normal acids, they react with, like typical acids reaction, metal plus acid, salt plus H2. You've got metal oxides and hydroxides, which are bases. They react with acids to produce salt and water. You've got metal carbonates, which are weak bases. They react to form salt, water, and carbon dioxide. You reacted with ammonia, which is also a weak base, to form ammonium salts. So acids have these typical reactions. Alcohols don't have those reactions because alcohols are such bad acids. So the only reaction that they usually have is a very, very slow reaction with sodium, where they end up forming a salt the H gets replaced and it turns into H2 gas. Is this clear?
Yes, sir.
The other thing, alcohols have just one very tiny, alcohols are not your typical acids. They don't act as acids, but they only have and their ionization, the ability to produce H plus ions is really bad. So you can't classify them as acids. They do release H plus ions, but if you have a million alcohol molecules, maybe one might ionize. So the ionization is really bad. And the only acid reaction that they have is with a metal and with a reactive metal, not just any metal, group 1 metal. These other reactions, they're not going to have those reactions. So यहाँ पे ना, we didn't want the OH to change, right? If we had added Na, तो OH would have reacted as well. Is this clear?
Sir, but why don't we want OH to change?
नहीं, क्योंकि we want to make this thing. I mean, we
Oh,
want,
okay.
ठीक है,
Yes.
we want this carboxylic acid to react, not the OH to react, ठीक है?
Okay. Yeah. Okay. Thank you.
Achha, 38 chlorine atoms in the upper atmosphere cause the breakdown of ozone. Which statements are correct when referring to these chlorine atoms? So, I mean, they are radicals. This is basically what they do because they they try to steal away oxygens. And so chlorine atoms act as catalysts. They're acting as a catalyst as well. They remain unchanged. Chlorine atoms are free radicals. That's also true. The chlorine atoms are formed by heterolytic fission of a covalent bond in CFCs, and that is also true. If a CFC goes into the upper atmosphere, strong UV rays will break the CCl bond, and that's what's going to happen. And it would not be heterolytic actually. Free radicals are never formed with heterolytic fission. They're formed with homolytic fission when the bond breaks equally and the Cl atom takes away its electron and turns into a radical. Remember, radicals are always formed during homolytic fission, not heterolytic. Is this clear?
Yes.
Yes, sir.
Achha, for this one, an unknown organic compound Z reacts with sodium to give a combustible gas as one product. Z does not give a yellow precipitate with alkaline aqueous iodine. So he's saying it reacts with sodium to metal plus acid produces a hydrogen gas. So alcohols will react with sodium. This alcohol would also react, and carboxylic acid would also react. We just discussed this. Okay? So sodium, metal will react with carboxylic acid, but also alcohol. And in each case, there would be H2 gas that would be formed. So now, what's the alkaline aqueous iodine thing? It's that's the Ideofoam test, and that is specifically used to identify two very typical structures. Remember, these two structures are identified by alkaline aqueous iodine. In that case, they give a yellow precipitate if this specific structure is present. What happens is that the CH3s in both cases, they're going to break off and they would form CHI3, which is the yellow precipitate. Or jo baki hai na, that's the rest, the remaining part, this carbon, in both cases, it would turn into a carboxylic acid. But since alkaline conditions are used, so a salt of the carboxylic acid would be formed, not the carboxylic acid, because the conditions are alkaline. So the carboxylic acid would react with the alkali. If the alkali is NaOH, then it would form the salt. So we're just looking for this structure. Who has that structure? And remember, it has to be a carbonyl group. So the first one, let me just start with 3 first. Propan 1-ol. Prop 1-ol it's got OH at the end. So that is not going to work. because you need a CH3. You need a CH3 right next to COH. We don't have that. So propane 1-ol is gone. Actually, that would be the answer. He's saying does not give a yellow precipitate. So that will give a negative test. So that means this is actually the correct one. TK, remember, it should not give a yellow. Pentane 3-ol would also. So pentane 3-ol. Pent is 5. TK, so it's going to be CH2, CH. Now again, over here, you need a methyl next to CHOH. You have a methyl which is next to CH2. You have a methyl which is next to CH2. So again, this would also be correct. I mean, it's not going to give a precipitate. And the first one is ethanoic acid. Ethanoic acid has the structure. But remember, it has to be a carbonyl group, not a carboxylic acid group. So this is also gone. It's not going to give a yellow precipitate. That means all three would be correct. Is this clear?
Yes, sir.
Tiga, remember this comes very frequently now. Ideofoam test, remember, it doesn't identify any carbonyl group. It only identifies a carbonyl group which has a CH3 next to it, or an alcohol, a CHOH, with a methyl group next to it. As a last question for this is, okay, there's compound X and it has the molecular formula C3H6O3. And he's saying heating X under reflux with acidified K2Cr2O7 forms this thing. So there's oxidation happening. So this one is, I think, 1, 2, and 3 carbon atoms. There's a carboxylic acid group over here. And I think there's a double bond O in the middle. So C, CO, and COH. So COH, CO, and COH. So that's the structure. And he's saying that reacting X with NaBH4, that's a reducing agent. Reducing agents, what they do is they reverse the whole oxidation. Wait a second. Heating X under reflux with the X gets oxidized to this thing. And when you try to reduce X, you get this thing. It's again 3 carbon atoms. The first one is an alcohol. The second one is also an alcohol. And the third one is also an alcohol. The rest are H. So he's saying, what is the possible structure of X? So let's start with the first one. The first one, I don't think the first one is possible. The first carbon atom is an alcohol. So that will turn into a carboxylic acid if you oxidize it. The last carbon atom is already a carboxylic acid. So if you oxidize it, it's going to remain unchanged. So you'll get the 2 carboxylic acid. The middle part is the one that's like, you can't turn it into a ketone by just oxidation. So that's not possible. So 1 is wrong. So 2, 3 would be correct, because all of these will produce these compounds. Aldehyde, you've got an aldehyde over here. So that would turn into a carboxylic acid. You've got a primary alcohol over here. That would also turn into a carboxylic acid. And you've got a secondary alcohol right in the middle. That would turn into a ketone. And this one as well. You've got a primary alcohol and primary alcohol on both sides. They would turn into carboxylic acid. And you already have a ketone in the middle. So this thing would be formed. Only the first one is the one that's going to be incorrect. TK, is that clear?
Yes, sir.
Yes, sir.
So we can try and do just one more question of a structured paper. 1 second, let me just, same year. This is M16 QP. So we'll start with the, one second, just let this open. So let's start with the last one. Or maybe the first one. So last से कर लेते हैं. अच्छा, you've got hold on. So you've got some reactions of C5. This is a compound P. अच्छा, इसके बारे में what is he asking? Give the structures for organic compound QRS and T. So you have to give the structures of QRS and T. The first thing is कि let's start with S first. KMNO4. ठीक है, remember it's strong, it's mild oxidation. ठीक है, so this is mild oxidation. What happens in mild oxidation? You've got an alkene. अच्छा, कितने carbon atoms are there? 1, 2, 3, 4, and 5. So I'm just going to draw 5 carbon atoms first. And there's a double bond on the second one, and there's a double bond right at the end. Not at the end. That's a 5. I didn't draw 5. Now I've got 5 carbon atoms. So mild oxidation is whenever you see a double bond, वो चला जाएगा, or in its place, there's going to be OH groups that are going to take its place. And a diol would be produced. That is simply mild oxidation. The other one is NaBH4. That is a reducing agent. What it would do is, and let me just discuss oxidation reduction very quickly, 1 second. Okay, this one over here. Remember this thing that aldehydes and ketones can be reduced back into secondary alcohols and primary alcohols. Okay, so primary alcohols can be turned into aldehydes, and they can be further turned into carboxylic acids. You have all these reagents for turning aldehydes into carboxylic acids and primary alcohols turning into aldehydes. But the reverse can be done with NaBH4 or LiLH4. So going back to this one, here's a ketone, and again it's 5 carbon atoms. So that's 1, 2, 3, 4, and 5. The ketone will turn back into an alcohol. The double bond would not be reduced. Remember, the double bond will not be reduced. Here's your Ideofoam test. What did I tell you about the Ideofoam test? You've got 5 carbon atoms. And this carbon atom over here is a CH3. So I told you that the CH3 will break off. This side will turn into a carboxylic acid, but since the conditions are alkaline, it would be a salt of the carboxylic acid. So, I mean, the H+1, I mean, there would be no OH over here because it's alkaline conditions. So this side turns into a carboxylic acid, which is this one. This other side would turn into a yellow precipitate of CHI3. And the last one is, what happens if you add hydrogen with nickel catalyst? What happens in that case is hydrogenation happens and the double bond. So you've got 3 carbon atoms and you've got a double bond. And you've got a double bond over here. Hydrogenation would happen, the double bond would turn into a single bond and H atoms will get added to this. So it will become saturated. There's another reduction reaction which happens with nickel and H2, and that is the ketone might also get reduced with hydrogenation. But I think since this reaction is not in your course at the moment, I'll open the marking scheme as well just to check. And just hold on 1 second. So this one. Okay, just confirming the last one. Which was the last question? So I think we were talking about Q, right? So they didn't turn the ketone into an alcohol, which it does actually, but since this is not in your, this reaction is not in your course, so they kept it as a ketone. So we're going to keep the ketone as it is. Hydrogenation only happens with the double bond. Is this all clear?
Yes, sir.
Yes, sir.
I said then the next part is I said this one is a difficult question, I think, if I remember properly. He's saying give the systematic name of compound P. So let's have a look. What was P? I said this one. So can anyone name this? What is this? It's 5 carbon atoms. What would you call this?
Serpent.
Yeah.
And two.
I said it's an as a first thing. It's a ketone, right? So
Yes.
it's going to be pentanone, right?
Yes.
I said now this AN over here represents whether it's saturated or unsaturated. So okay, is it unsaturated or saturated? It's got a double bond. Unsaturated. It's got.
P. Sorry, P. Yeah.
I said it's going to be. It has a double bond. So ये AN नहीं होगा. It will actually be EN. Is this clear? ठीक है. अच्छा, then you have to give the numbers. Okay, who's more important, double bond or ketone?
Ketone.
ठीक है, ketone. Ketone is more important. So you're going to start your counting from this side. You have to give ketone the smaller number. So ketone is at position number 2. And wo jo EN alkene, the double bond is at position number 3. Okay, dashes, add the dashes. So that's your name. Is this clear?
Yes.
Yes.
As a the next part, that was the one that was difficult. You've got, as we're done with, what would you observe when B reacts with 2,4-DNPS? That's a test for ketone. So you'll get an orange precipitate. Remember carbonyl groups, any aldehyde or ketone is going to give, that's a test for identifying whether a compound is a carbonyl compound or not. So now this one is going to be slightly tricky. You've got this one was a difficult question. If this is the same question, you've got C5H8O. That's the formula. And he says, first thing, he says it's got, let's underline, U contains a chiral center and has the same molecular formula. We do have the molecular formula. It decolorizes bromine. What does that indicate? What does it have? Saturated or unsaturated?
Unsaturated.
Okay, so it has a double bond. So it is chiral and it's got a double bond and does not show cis-trans isomerism. So it has a double bond which should not show cis-trans. Because double bonds are the ones that actually show cis-trans. And then you have when U is heated under reflux in the presence of excess acidified potassium dichromate 6. So this is oxidation happening. So this is the organic product of the oxidation. So let me just go through this. Did we miss any other information? So this is the organic product of oxidation. Remember, this is the product. By looking at the infrared, you should be able to just spot directly. You don't even, train yourself not to even use the data booklet, but I'll just open the data booklet. Remember 2 bonds. There are 2 bonds that are easily identifiable, which you should, I think, memorize. Because those are the only ones you can actually figure out, because infrared spectroscopy otherwise is kind of useless. You can't really figure out a lot of important stuff from infrared spectroscopy. So just make sure you know this. The only thing you can clearly identify is a serial bond O, because it has a very clear absorption, a very strong absorption that's not overlapping with any other thing. Okay, so if you look over here, there is a serial bond O. You've got a strong absorption at this, so that indicates there's a serial bond O. The other absorption that you're going to see is it's this broad absorption that you get around 3000 and before 3000, and that's your OH, carboxylic acid OH. This one, 2500 to 3000. It's a strong and very broad absorption. So remember, it's a carboxylic acid OH. You get not just any OH, but a carboxylic acid OH. So that means you got both things. This one is basically a carboxylic acid. Okay, there's a acetyl bond O, which is this one, and there's a OH of the carboxylic acid, which is this one. Is this clear?
Yes, sir.
Achha, so the oxidation product is a carboxylic acid. That means your original molecule might be a primary alcohol or it might be an aldehyde. Taaki wo forward it goes and forms carboxylic acid. So the oxidation product is a carboxylic acid. So this must be a primary alcohol. I mean, you've got two options for this. So it might be a primary alcohol or it might be an aldehyde. Is this clear?
Yes, sir.
So now we can start. Now you have to, based on this, draw U. Okay, so now that would require a lot of trial and error. First thing, 5 carbon atoms. You have to make it chiral somehow. So how can I make, and I need to put a double bond in there somewhere as well. So first thing, if I put a double bond somewhere in this, I said the double bond should not show cis trans. I said, how do I make this, make any carbon atom chiral? So what I can do is 5 carbon atoms, right? So there's an H on one side. Let's put one carbon over here. And a carbon, double bond carbon over here, right? Now this is, at the moment, this is not chiral because the 2 carbon atoms are kind of the same. So I know that it could be an alcohol or an aldehyde. So what I can do is maybe I can add an OH. Okay, now the two sides are different. Remember, I can only add one OH because there's only one oxygen. The other thing I can do is, because I've still not figured out whether it's an aldehyde or an alcohol. You clear? Is this clear?
Yes, sir.
Yes, sir.
So the other thing I'm going to do is I'm going to try an aldehyde as well. Okay. Anyways, I wanted to make this chiral. I mean, that's the only way I can make it chiral. Maybe the OH group is somewhere over here. Maybe the aldehyde is on the double bond. I think that's the only information we've got. Sorry, it's do we have any other information? The double bond must not show cis trans. So if it's at the end, it will not show cis trans. That's also fine. I'm going to add in the hydrogens. So there are 8 hydrogens. So how many hydrogens do we have? 1, 2, 3, 4, 5, 6, and 7, and 8. I think it's going to be this one. Okay, the other one will have more hydrogens. If I go for an alcohol, a primary alcohol, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it's going to be this one. Okay, that's the molecule. It has a double bond. It's chiral as well. It's an aldehyde as well, which will get oxidized to form a carboxylic acid. So I think it's this one, and we can check this one whether this is the right one or not. Okay, and it is the right one. It's the same one. Carbon, a CH3, 2 carbons over here, double bond, and an aldehyde on one side. So it is exactly the same one. CH3 on one side, 2 carbons on one side with a double bond and an aldehyde on one side. So that's it. Okay, you clear? Any question?
No, sir. No question.
No, sir. No question.
Chalo, theek hai. Let's continue next time then. Okay?
Okay,
Okay,
sir.
everyone.
Allah Hafiz.
Take
All
care.
right, sir. Thank you.